Overland flow on hillslopes may be caused by rainfall intensities, per hour, exceeding the saturated hydraulic conductivity, Ks, per hour, of a topsoil or other surface horizon, equivalent to the infiltration capacity or coefficient of permeability of the topsoil. This rapid pathway of rainfall towards stream channels is called infiltration excess overland flow. If rainfall is reaching the ground at a rate less than the saturated hydraulic conductivity of the topsoil, but cannot infiltrate because the topsoil is already saturated as a result of drainage from upslope areas, then the rainfall onto these saturated areas will move as overland flow across the surface. This pathway is called saturation overland flow by direct precipitation or SOF by direct precipitation. If the downslope subsurface flows exceed the ability of the downstream soils to discharge them directly into a stream channel, then subsurface water may emerge from the topsoil onto the ground surface as return flow. This return flow may then travel overland towards a stream as so-called saturation overland flow by return flow, SOF by return flow. Soil types that typically have a lower saturated hydraulic conductivity have a greater likelihood of generating infiltration excess overland flow, and were present in downslope areas, also a greater likelihood of generating surface flows by saturation overland flow by direct precipitation and saturation overland flow by return flow. The soil type called a Gleysol using the International Soil Classification System or GLey within the Soil Survey of England and Wales, SSEW, soil classification system typically exhibits lower saturated hydraulic conductivity values throughout UK soil profiles. Table 2 shows an example KS profile for a gley in the Lune Valley, northwest England, UK. These measurements were undertaken in the field with a ring permeameter, a technique demonstrated to give accurate values, even for disturbance-sensitive gley soils. Horizon-specific saturated hydraulic conductivities, cm per hour, of a humic Gleysol near Farleton, Lancashire, UK, after. Soils in England and Wales that are classified as gley cover a range of soil associations based on the SSEW. As a result of their greater likelihood of generating overland flow, these gley soils are classified as having Innsprost 1 value in excess of 50%. Enhancing the permeability of such soils could have the greatest impact on reducing overland flow across catchments and thereby have the greatest potential to reduce flood peaks in rivers. As a result, tree planting to increase soil permeability includes areas with such gley soils. Consequently, for NFM modeling a key need is to represent the permeability effects of planting deciduous trees on gley soils. Very few UK studies are available that quantify the difference in soil Ks of gley soils beneath deciduous trees relative to that beneath adjacent grasslands. These few studies are summarized in Table 3 and give a range of 1.5 to 3.5 factor increase in permeability for deciduous tree planting on gley soils. The Ks factors in the first column of Table 3 were then used to provide the fuzzy set of parameter changes in the dynamic top model scenarios. Ratio of Ks measured for deciduous trees to that grassland growing on gley soils in the UK. 1 factor difference in Ks, i.e. Ks below deciduous trees / Ks below grassland. 2 subsoil association from Soil Survey of England and Wales. 3 results of related study of Carroll et al. Rejected on basic quality assurance criteria, i.e. absent sampling size per land cover, absent information on frequency distribution, etc. This observed increase in permeability for gley is smaller than the factor of 5 difference between predominantly deciduous woodland and improved pasture recently observed on well-drained Utrecht Gleysol, brown earth, soils in Scotland by Archer et al. The observed effect on gley is also smaller than the effects observed on other soil types across the globe, the majority of which are between 2 and 20, with some outliers much greater than this, which is likely to be due to macropores along root channels. In any event, if the roughness of these high runoff areas can be increased through roughening up, then it may be possible to attenuate quick flow from these soils until they become saturated by deficit filling. Critically, it should be remembered that most of the stream hydrograph during floods comprises water that has primarily traveled to the stream via subsurface pathways. Effects of trees on Ks might not be isotropic, but we have even less information on downslope Ks. Even within very flashy, but undisturbed tropical streams, only small proportions of flow within the basin have been directly measured as overland flow, for example 10 square kilometers, The prioritization of areas to model in more detail and through using Monte Carlo simulations was considered essential to understand more about uncertainty and build on the screening level modeling with flow, despite its high resolution. The detailed modeling was therefore calibrated against an observed series of extreme events, November DEC 2015, within 3 severely impacted catchments up to 223 square kilometers in the area within Cumbria, UK. The results from one of these catchments, the Upper Kent, 90 square kilometers, are used in the following sections to illustrate the approach that was taken for all 3 catchments. Lancaster University has recently developed an extended and flexible implementation of the Dynamic TOPMODEL model, first implemented in Fortran by Bevan and Freer. It is an extension of the popular TOPMODEL applied in many studies. Dynamic TOPMODEL employs the efficient parameterization scheme of TOPMODEL, but allows a more general approach to a grouping of points in a catchment for calculation purposes, based on overlays of characteristics rather than simply the map of the topographic index. All the model parameters needed to run the model are shown in Table 4, along with typical ranges of values applied in this project. Figure 9 provides a perceptual overview of Dynamic TOPMODEL. Parameter ranges / typical values within Dynamic TOPMODEL, after ref. Schematic of Dynamic TOPMODEL. It is a semi-distributed hydrological model that utilizes areas of similar hydrological behavior called HRUs, hydrological response units. These units may be in the evaluation of NFM divided to represent distributed interventions within the landscape. It has sufficient complexity to represent the key catchment processes, notably subsurface and overland flow pathways, and there is some evidence to link NFM measures to alteration of the parameters, for example transmissivity distribution, representing these processes. Its simple structure allows efficient operation, allowing thousands of model runs to be simulated to investigate uncertainties and sensitivities. Overland flow velocity is fixed throughout each unit and can be changed to reflect changes in surface roughness introduced by, for example, peat restoration or riparian tree planting. The maximum transmissivity at complete saturation T02/ is a measure of the local maximum saturated downslope transmissivity per unit hydraulic gradient, where transmissivity is the integral of the permeability to the saturated depth. This is a key parameter in identifying the onset of saturation overland flow, SOF. When downslope flows into lower slopes filling remaining storage capacity, return flow is produced. SOF is also generated when rain falls onto these areas of already saturated ground. An exponential transmissivity profile is assumed. The use of such a form is supported by experimental evidence and reproduces the typically higher values of permeability found near the ground surface. The recession parameter M controls the rate of decline of transmissivity TA's water table reduces. Small values of M lead to very rapid declines in transmissivity, suggesting shallower, faster responding streamflow generation systems. Deeper active hydrological systems are represented by a slower decline in transmissivity. Dynamic TOPMODEL routes subsurface flow downslope between HRUs using a routing matrix derived from the local topography. It is assumed that the local slope is a reasonable approximation for the hydraulic gradient. The root zone storage SRs max must be filled before any water table recharge begins through incident rainfall. Transpiration, and soil evaporation, is removed from this zone at a rate proportional to the actual storage. Direct observations of soil moisture content are unavailable for the catchments in the period simulated, so a reasonable initial value was applied, SRZ0 equals 95%. Dynamic TOPMODEL represents an intermediate level of complexity that incorporates the key hydrological processes, but without imposing too many assumptions resulting in a large number of parameters, related to say soil properties, for which we do not have direct measurements. The model was also selected because of it makes use of standard data formats for catchment topography, elevations, channel network, and relevant spatial data such as land cover. Presents results back to the landscape as well as formats such as streamflow hydrographs that are easily understandable by partners. Uses real, spatially distributed rainfall data and can be rapidly calibrated against real event data, allowing for data quality.